I'm really excited to be here, and it was really great to follow that demo. That was such a cool demo. But I also share the passion for using biology to grow materials. And so I'm going to tell you just a little bit about some of the materials that we use biology to make. So this is about inorganic materials. So just like in the last demo, when you heard about how organisms can be used to make carbonates and used to make cements, I've been fascinated with abalone. Abalone are a biocomposite material that's a marine snail that makes these incredible shell-like structures. These shell-like structures are made on the nanoscale. So the organisms have the DNA sequence that code for a protein sequence that make exquisite materials on the nanoscale. They do so in ocean temperatures, ocean pressures, and they don't use toxic materials, and they don't add toxic materials back into the environment. And organisms have been making amazing materials for billions of years, like proteins and cells. They've been making hard materials like shells and diatoms for hundreds of millions of years. But what I've been doing in this DARPA program is engineering organisms to make materials through evolution they've never had the possibility to work with yet. So how do you do that? How do you get an organism to make a material that it's never been in contact with before? And so organisms in the ocean, or organisms like us, use calcium, and they use silicon and iron to make materials. So they have a DNA sequence to have proteins that can actually grab ions out of solution and build these structures in a very programmed way. So we use simple organisms like viruses. This virus is called a bacteriophage, which only infects bacteria. It has single-stranded DNA, and that single-stranded DNA codes for the proteins that make it up. This red structure here is a model of a bacteriophage, and see how it has these beautiful alpha helix-like proteins that are crystallographically related to each other. Now think about if you could have this virus and you could engineer it to make any material you wanted or interact with another atom or element on the periodic table. So that's what we do. And we do it through combinatorial chemistry. So we take a billion viruses that are all genetically similar to each other, and we encourage them to work with the rest of the periodic table. And from there, we can get them to start to grow materials. Well, it sounds crazy, but it's possible. Just like you saw in the last demo, we have viruses that make battery electrodes, like this sodium-ion battery electrode. We have viruses that can make materials for catalysts and solar cells and building supplies. So I was really lucky to be part of a DARPA program called the 1,000 Molecules Program. And I'm a biological engineer and I'm a material scientist. But as a material scientist, I got to make as many materials as I wanted to make using biology. And so we made at least 110 biologically programmed materials during this program. And we used it for energy storage and catalysis, environmental remediation, magnetic materials, toxic chemical removal, and solar cells and energy conversion. And I'm going to tell you just about one application that we used. This application I wasn't expecting at all. So I showed you the battery electrode already. But we were working on making high surface area carbon materials using viruses. So using genetics and programming the virus to have certain amino acid sequences on their proteins, we actually used it to make really high surface area carbons that are on the order of about 2,000 meters squared per gram. And now imagine a virus with these beautiful proteins on it, and the proteins actually doing the chemistry to knit together these high surface area carbons. And now we can add all other kinds of materials to it. We can add metal oxides and catalysts. And so we were doing this in the lab, and we were showing that it was really good at binding to toxic materials. And so we collaborated with the Army, CCDC, to say, what else would these be good at being able to clean up? And so we looked at being able to do environmental decontamination. We looked at chemical threats and biological threats. And they took it from being able to grow milligrams in our lab to growing multiple kilograms in their lab, and they scaled it up. So from there, we can make textiles, we can make filters, we can make fabrics that have these genetically engineered materials in them that can decontaminate or bind to materials. Oh, they can also store gases. You can think about them, use it to make a backpack that could be a gas container for air or oxygen. You can think about it as a way of storing methane in a smaller container. And so I brought just a sample of what some of these biomaterials look like that are made into a textile. You can imagine using these for a mask. You can imagine using them for clothing. They not only are really great at absorbing toxic materials, but they're also good at decontaminating them, because we can put catalysts in there that are specific to break down compounds we want to be able to make. And working with my great collaborators in the Army, we've now scaled it and looking at many different kinds of applications. So in addition to translating it for DoD needs for the warfighter, we've also started a company because we found that they're also really good at breaking down PFAS, or fluorinated carbons that are contaminating water. So I guess I just want to leave you with biology is incredible at being able to be programmed to make many different kinds of materials. We've made at least 110 in this program, and we've developed a few of them and translated some of them as well. But there's so many more possibilities that you can use by taking advantages of millions and billions of years of evolution to encourage biology to work with the rest of the periodic table and build things on the nanoscale and the microscale that can have an impact on the planet. I have you can look at these outside and I'll answer questions. And I also have a model of what the bacteriophage looks like if you want to be able to take a look at it. So I'm happy to take questions after this session. Thank you for your attention.